Welcome you all. Bismillahirrahmanirrahim. Dear students, welcome you all to the industrial formation class. This is the class related to the new chapter, that is milling, and in today's lecture we will start a topic from the introduction of the combination or milling, that is also termed as size reduction, and we will discuss in this lecture about the brief introduction of this particular size reduction, its importance and the reasons and factors affecting combination. In today's lecture we will also discuss the methods of particle size analysis, and this part of the lecture we will discuss one of the popularly and widely used method, that is termed as sieving. Dear students, the main objective is to learn about the combination, that is also termed as particle size reduction or milling. The main focus is to learn about introduction of the combination, and the reasons are the main objectives, that why we focus the combination or the particle size reduction process and the industrial pharmacy, and the various factors which affect the particle size reduction. And the second part of the lecture we will discuss the various methods of particle size reduction and the analysis, including one of the method that is termed as sieving. Dear student, after the completion of this lecture you will be able to learn about the process of combination, its introduction, and the various factors which affect the process of particle size reduction or milling, and the different methods of particle size analysis. Let's discuss the introduction of the combination of particle size reduction. Combination, which is also termed as milling, can be defined as the mechanical process of reducing the particle size of solid. Certain other terms which are used for the process of milling are combination or size reduction, including crushing, disintegration, dispersion, grinding, and pulverization. These are the other terms which are used for the process of particle size reduction of solid material. In the pharmaceutical industries, it is one of the routinely used process to reduce the particle size of the solids, because it is very much essential and widely applied process. And some of the pharmaceutical applications of milling include, if we are interested in the particle size reduction, that we are increasing the surface area for some materials and some therapeutic compounds or medicinal compounds. There is issue of the solubility, and due to their poor solubility their effect is not enough or efficient, so their particle size is reduced in order to increase their surface area, and surface area per unit weight, that is known as specific surface. We can increase the surface area of the material by decreasing the particle size. If we reduce the particle size, of a solid material, it is consequently resulting in the enhanced surface area, and this particle size reduction, which is responsible for the increasing the specific surface, affects the therapeutic efficiency of the low solubility medicinal compounds. That's why nowadays the research is under process for the particle size reduction to the nano size material up to the nano size range in order to increase the low solubility of medicinal compounds, because due to their low solubility the compounds have poor efficiency or efficacy. For example, there are several drugs in the market nowadays which having the poor solubility problem, and some of the products includes the cyclophenolic, which is one of the NSAIDs, and glimepiride, which is anti-diabetic drugs, and these are also examples of the low solubility medicinal compounds. So one of the way to increase the solubility of these poorly soluble medicinal compounds, the surface area or specific surface is enhanced by particle size reduction to the nano size range. Increased antiseptic action for calomel ointments. It is one of the ointments named as calomel ointment, having antiseptic action, and its action, that is activity as antiseptic, that is the enhancement in this activity, that is antiseptic activity of calomel ointment, is due to reduced particle size. And this example, the calomel ointments increased antiseptic action is due to the reduced particle size. Particle size may also affect the texture, the taste, and rheology. Rheology is the flow properties of matter, and the flow properties of the oral suspension in addition to its absorption. Not only the texture is affected by reducing the particle size, but also the taste and the rheology, that is the flow properties of the oral suspension, is affected as we reduce the particle size. Moreover, the absorption is also affected, because if we reduce the particle size, their solubility and their texture, their taste, rheology, in case of the oral suspension, and ultimately the absorption will be optimized. Extraction from animal glands like liver and pancreas, and from crude vegetable drugs is facilitated by the process of particle size reduction. If we are interested in to extract from the animal glands, if we reduce the particle size and we cut into pieces to that animal gland like liver and pancreas, and the extraction process will be facilitated. Similarly, in case of the crude vegetable drugs, if you want to extract some of the contents and we reduce the particle size, or the milling process is done for that crude vegetable drug, then extraction will be easy and enhanced. Another application is the drying of wet masses. If we want to dry the wet mass or the material that is having moisture content, and we want to dry it, and the wet mass drying will be facilitated by particle size reduction. If we reduce the particle size of the wet mass and then we dry, then the process of particle size reduction will be facilitated, and the particle size reduction will facilitate the drying process. As you know that we have discussed in detail and the theories of drying, that the drying involves both heat transfer and mass transfer, and the heat transfer by various ways and the mass transfer by the process of diffusion will be favored if the reduced particle size of the wet mass is processed prior to the drying, because after the milling process the surface area will be increased, and the reduction in the distance that the moisture will travel within the particle to reach the evaporating surface or the outer surface will be minimized or reduced. So the evaporation process will be easy, the rate of drying will be easy, because the moisture will travel less distance in order to reach the outer surface, that is the evaporating surface. The mixing of several solid ingredients of a pharmaceutical product of pharmaceutical processing is easier and more uniform if the ingredients are approximately the same size, and if we reduce the particle size of the ingredients and then we want to mix the several solid ingredients in the pharmaceutical dosage form designing, then the process of mixing will be favored. A fine particle size is essential for proper function of lubricants. For example, one of the lubricants, that is magnesium stearate, it is used in the tablets, the compressed tablets and capsules. If we want to encapsulate some of the products and the proper function of the particle size, that will be one of the prominent essential part of this formulation. And the function will be enhanced by the ability to coat the surface of granulation or powder. If the particle size is fine, then these processes of the encapsulation, the compression of the tablets will be proper functioning, and the ability to coat the surface of granulation or the granules or the powder coating will be favored. Particle size reduction, there are different types of the equipment which are termed as milling equipments, and we want to classify the milling equipments on the basis of the particle size reduction. There are three main classifications. On the basis of that we classify the equipment. The first one is coarse milling. Some of the equipments that is resulting in the process material that is of the coarse milling that produces particles larger than 20 mesh, and similarly intermediate milling that produces particles larger than 200 to 20 mesh, and that is 74 to 840 microns equivalence, and the fine milling produces particles smaller than 200 mesh. This is the classification of equipment on the basis of particle size reduction, producing coarse particle, intermediate particle or fine particle. On the basis of these we say that coarse milling, intermediate milling or fine milling is done by the equipment. In this part of the lecture we will discuss the different factors affecting the particle size reduction. There are several factors which affect the particle size reduction. One of that is hardness. Hardness is a property of the material, that is the surface property of the material, and a arbitrary scale of hardness has been devised known as Mohs scale. and determine the hardness. It is less hardened, also it is a tough one. At the top of which is diamond, and the diamond is the hardest material with more hardness, that is more than 7, and the scale of the Mohs, that is the hardness of the diamond, is 7, more than 7, which is a surface so hard that it can scratch anything. It is the hardest material. At the top of the scale of the Moh, that is more than 7 Moh hardness. At the bottom of the table with more hardness, that is below that range of the Mohs scale. And this scale, the material that is having the top of the scale, which is your diamond, and that having most hardness more than 7, it means that it is a hard material and it can scratch anything. At the bottom of the table in this Mohs scale, that is a Mohs hardness less than 3 stock, which is soft enough to be scratched by anything above it. A material having more hardness less than 3, example is stock, and the material having value above this can easily uh, scratch this material, that is talk. The hardness on this scale, either that is the top or the low one or the bottom one, the harder the material, the more difficult it is to reduce the particle size. It means that the harder material is difficult to reducing the particle size of that particular material if the material is hard. The second factor that affect particle size reduction, that is material structure. Some substances are homogeneous in character and some are not homogeneous, and mineral substances may have lines of weakness along which the material splits to form flake-like particles. Vegetable drugs have a cellular structure often leading to long fibrous particles. So particle size reduction also depend upon the material structure. The third factor, that is abrasiveness. Abrasiveness is a property of hard material, particularly those material which are of origin, that is mineral origin, and it may limit the type of machinery that can be used. During the grinding of some very abrasive substances, the final powder may be contaminated with more than 0.1% of metal won from the grinding mill. Because of the abrasiveness nature of the material, because of the property of the hard material of the mineral origin particularly, and the striking of this particular hardness material and abrasiveness property of the mineral origin material, the grinding mill in which it is grinded and the particle size is reduced, the mill part, the metal, that is the composition of the mill, will be worn from the grinding mill, in which the material of the mineral origin or the material having the abrasiveness property is processed in the material in that particular mill, and in this case contamination will be more than 1% caused by this abrasiveness type of material. Another parameters or factor that is termed as softening temperature. During size reduction process, sometimes heat is generated which may cause some substances to soften, and the material becomes soft, and the temperature at which this occurs can be important. Like mixing material such as stearic acid or drug containing oils or fats are example that may be affected. Because of the generation of heat, The waxy material or certain other types of material is affected due to the generation of the heat during the process of particle size reduction. Some methods can be used to overcome this, like cooling the mill in order to avoid the temperature increase, either by water jacket or by passing a stream of air through the equipment. We want to reduce the temperature and to cool the mill, that is one of the way to minimize this effect. Moisture content also affect the particle size reduction or milling. It is found that material don't flow well if they contain between 5 to 50% of moisture. If a material or the solid material we want to reduce the particle size and having the moisture content in the range of 5 to 50%, then the materials will face difficulty in the flow. Under this condition, the material tends to reduce the cake together in the form of balls because of the moisture content. In general, grinding can be carried out satisfactorily outside these limits. So, for this purpose, below 5% material having moisture is suitable for dry grinding, and the material having moisture content greater than 50% is subjected to wet grinding. Because of the high content of the moisture, the material is not subjected to the dry grinding, and the appropriate process of the particle size reduction will be wet grinding. Crushing strength is the greatest compressive stress, that is a brittle solid can sustain without fracture, and that is another parameter for the affecting the particle size reduction. The power required for crushing is almost directly proportional to the crushing strength of the material. Fiability, as you know, the fiability, that is the loss of the mass. The fiability of material has its tendency to fracture during normal handling. In general, a crystalline material will break along well-defined planes, and the power required for crushing will increase as the particle size is reduced. Stickiness is also one of the factors affecting the particle size reduction. A sticky material will tend to clog the grinding equipment, and it should therefore be ground in a plant that can be cleaned easily, because in order to prevent the clogging of the grinding equipment or mill, pharmaceutical materials that are gummy or poisonous in nature may be troublesome, particularly if the method used for particle size reduction generate heat. Now, in this part of the lecture, we will focus on the methods of particle size analysis. Naturally occurring particulate solids and mid solid, the shape of particle is irregular. There is not proper shaping of the particles in case of the naturally occurring particulate solids, and the size of the particle varies when the range of the largest and the smallest particle. There is no known method of defining an irregular particle in geometric form because the shape is irregular. However, statistical methods have been developed to express the size of an irregular particle. If we have a regular shape or proper shaping of the particle, then it is convenient to determine the dimension in a single term. But in this case, as the irregular particle, so it is difficult to express it in a single dimension. So, for an irregular particle in terms of a single dimension, we have to use the statistical method that is referred to as its diameter. For convenience of mathematical treatment, An irregular particle is considered in terms of an equivalence pair. We are considering that this irregular particle is equivalent to the spherical particles, and the size of the particles can then be expressed by a single parameter, that is diameter. The volume of particles may be determined by displacement of the liquid, as the volume of a sphere is pi d cube under root 6. The equivalent diameter of an irregular particle with a volume V is equal to, by using this equation for the diameter of the irregular particle. Now, methods of particle size analysis include some of the methods: microscopy, sieving, electrical stream sensing zone method. One of the method in the electrical stream sensing zone method is called counter method, sedimentation method, and other methods using the X-ray diffraction method. Microscopy is the most direct method of particle size distribution measurement. For white light and a daily light is used to measure the particles from 0.5 to 0.4 to 150 microns with special lens using and UV light using the lower limit, that is 0.4, may be extended to 0.1 micron. We can reduce that into the more, it is 0.1 micron. It is by using special lenses. The size range of ultra microscope is from 0.01 to 0.2 micron. In this case, it is ultra microscope is used, and the range is reduced further. The diameter of the particle on the slides are measured by means of a calibrated Pylar microscope high speed, that is calibrated already. And this is one of the microscopy diagram and the microscopy for particle size analysis. Then the particle image and the lens and the variable aperture width and the light source that is applied, and the photomicrograph is shown of that particular particle for which the particle size analysis is to be done. The second method, that is sieving, it is the most widely used method for measurement of particle size distribution because of several reasons, and these reasons includes because sieving method is inexpensive, it is simple one, and it is rapidly used with little variation between operators. And the limit of this sieving method is 50 to 10 microns. The procedure involves a simple procedure, that is mechanical shaking or agitation of sample, for which the particle size reduction, particle size analysis is to be determined through a series of successively smaller sieves and the weighing the proportion of the sample retained on each sieve. Sieving or screening is a method of separating a mixture of particles into two or more size fractions as well. The oversized materials are trapped, and the material having the larger size will be trapped above the screen, while undersized material can pass through the screen or mesh. Sieves and screens are usually used for larger particle size material, for example, that is greater than approximately 50 micron, that is equivalent to 0.050 millimeter. And the size equivalence scale, there are two scales that are used to classify particle sizes are one scale is US sieve series, and the second one is termed as Taylor equivalent, and sometimes the Taylor equivalents are also called Taylor mesh size or Taylor standard sieve series as well. And this is the table for the US sieve series presentation of the standard US sieve sizes and the Taylor mesh sizes. On left side you can see the US sieve sizes and Taylor mesh size, as well as the opening and millimeter and opening and inches, and that particular relevant table you can see the US sieve sizes. For example, number 3.5 sieve size, and that is equivalent to 3.5 of the mesh size of the Taylor series, and the opening is 5.66, that is in millimeter, and it is equal to 0.233 inches. Similarly, in the Taylor sizes, Taylor standard. 3 mesh and 2 half mesh are included, but these are lacking in the US Sieve series. And so on, you can see from the top to bottom up to mesh number 400, that having Taylor series as well 400, and opening in millimeter, that is 0.037, and in inches 0.0015. From top to bottom, when the sieve size is increases, it means that the mesh or sieve per square inch will be increases, and larger particle will pass from the top one compared to the lower one. References for this lecture I have consulted Lakeman Leberman, The Theory and Practice of Industrial Pharmacy, 3rd edition, pages 21 to 29. Alton Pharmaceutics, 2nd edition, The Science of Dosage Form Design, and as well as Cooper and Guns, Tutorial Pharmacy, 6th edition. Inshallah, we will discuss this lecture in the online Google Meet session as well.